Hello everyone, welcome to Chemistry Workshop. In this episode, we'll examine the elegant synthesis of cyclobutastellettolide B by the Young Group in 2021. In literature, chemical composition and activity of sponges in Vietnam have been studied since 2006. According to a survey in 2019, over 250 compounds have been isolated from over 30 species of sponges, with some of them exhibiting extraordinary potential for cancer cytotoxicity and anti-inflammatory uses. Immediately after this survey, another two novel terpenoids with an unprecedented carbon framework are discovered in an unclassified Stella sponge. These two terpenoids possess a 19-carbon framework with a tetracyclic core with 3 contiguous quaternary stereocenters. In addition, one quaternary stereocenter is shared among 3 rings, and steric factors could be a great hindrance to the construction of this stereocenter. On the other hand, not only is the total synthesis of this terpenoid important in developing new synthesis methodologies and strategies, this compound is also of pharmacological importance. It is found to significantly increase the production of reactive oxygen species in murine peritoneum macrophages. Reactive oxygen species are found to regulate T-cell immune response in tumors, so it could be a potential to be an immunoregulatory agent. Furthermore, reactive oxygen species are found to involve in redox signaling pathways in driving angiogenesis, the process of forming new capillaries from existing blood vessels. Moreover, reactive oxygen species are key reactive species in photodynamic therapy, exhibiting cytotoxicity against tumor cells and could be a potential anti-neoplastic agent. Also, the carbon atom numbering is provided for future reference. We will start with a retrosynthetic analysis of cyclobutastellettolide B. Through great insight, the group anticipated a biomimetic type 2 Norrish reaction, a Norrischian cyclization, with concomitant lactone ring closure could afford 1 from 2 in one step. However, the steric factor around C9 could bring great difficulty to the cyclization, and the selectivity of C9 against C7 and C17 could also present itself as a possible problem. Still, proceeding from 2, it could be attained from 3 with a Wittig reaction and further oxidations, which could be produced from 4 through alkylation and oxidations. Noticing the gamma-delta unsaturated ester moiety present in 4, the group anticipated that Johnson-Claisen rearrangement from allylic alcohol 5 could be the path to the formation of 4. Then, the ring structure of 5 can be formed through a cascade cationic cyclization from epoxide 6, akin to the cyclization of squatting outside, and 5 can then be formed through hydroxymethylation. Then, 6 could be a reasonable starting point for this synthesis, since it could be synthesized in 5 steps from the starting material, geranoacetate, from published procedure. The synthesis of cyclobutastellettolide B starts from geranoacetate. Geranoacetate is first subjected to a sharpless asymmetric dihydroxylation with a catalyst DHQD2-FAL, resulting in a diol with C3 receiving the R configuration. Then, aiming for an epoxide, the group selectively mesolizes the C3 hydroxyl to a mesylate, which is then attacked by the C4 hydroxyl and fashions epoxide 8 with inverted configuration at C3. Then, the epoxide 8 is subjected to mesylation and then cross-coupling with lithium trimethylsiloacetylide, forming 6, which is perfectly suited for tandem cationic cyclization. Intermediate 6, possessing multiple unsaturated bonds, is a potential site for polycyclization. With the introduction of a Lewis acid, namely titanium tetrachloride, 6 immediately cyclizes to 9 as the bromine captures the cationic intermediate. Then, a lithium halogen exchange with tert-butyl lithium results in an alkyl lithium species, which then attacks DMF and is reduced by sodium borohydride, result in allylic alcohol 5. Following the retrosynthetic path, 5 is then exposed to pivatic acid and triethyl orso acetate and undergoes a Johnson-Claisen rearrangement to obtain the double bond and the tethered ester group, and attaching an acetyl group to the hydroxyl at C3 furnishes the intermediate 4. The Young group tried out a lot of methods to introduce the methyl group at C8. First, the group tested out a possible hydroboration on a double bond and an oxidation alkylation to obtain the aldehyde group with alkylation at C8, but a hydroboration process also reduced the ethyl ester group at C12 to a primary alcohol. Then, they explored more methods to install the methyl group at C8. They tried to form an alloalcohol, performing a Simon-Smith cyclopropanation and then opening a cyclopropane ring to install a quaternary center, but the bad diester selectivity in this pathway of the cyclopropanation prevented this pathway to be a useful method to form the quaternary center. Then, the group tried to introduce the aldehyde first through treating 11 with a Lewis acid to get 14, and then established a quaternary center at C8. However, due to its steric bulk surrounding C8, the attacking methyl aldehyde formed a methyl vinyl ether instead, and the group had to explore alternative methods. Then, the group attempted to use the vinyl ether 16 formed by treating the aldehyde 5 with beth-trimethylsiloacetamide with DBU with a cyclopropanation and oxycyclopropane ring opening strategy to furnish the quaternary center. After forming the vinyl ether 16, the group performed a Simon-Smith cyclopropanation to form the cyclopropane ring in 17 with excellent selectivity for the 1,3-diaxial strain from the ring methyl group, and the 1,3-allylic strain from the vinyl ether group hindered the attack from the top side. The cyclopropane ring opens to form an allylic cation, which immediately tautomerizes to the aldehyde 3 with proper configuration at C8. Then, 3 is subjected to a Wettig reaction with ethyl triphenylphosphonamide to smoothly form alkene 18. And then, alkene 18 undergoes upjohn dihydroxylation and Swern oxidation, which furnishes 1,2-diketone 2, the precursor needed for the Norris-Young cyclization. Then, to complete the synthesis, 2 is exposed to UV radiation, and through the biradical intermediate 2B produced after a 1,5-hydrogen abstraction, the cyclobutanol motif is formed, which is immediately followed by the attack of the ethyl ester moiety to produce the lactone ring and the final product 1, cyclobutastellettolide B. To explore the reason behind the selectivity of C9 against C7 and C17, the group explored the computed barrier in the cyclization of a similar molecule and cyclobutastellettolide B. The group computed the barrier for forming biradical for cyclobutastellettolide B and its derivative with the ester group as C11 and C12 replaced with the methyl group. The 1,5-hydrogen abstraction at C9 has a lower barrier than abstraction in C7 and C17, and is also quite exothermic and has a low tendency to undergo a reverse hydrogen abstraction, while the abstraction at C7 and C17 are both reversible. In addition, the role of the ethyl ester group stabilized the product through hydrogen bonding, but not by much, since this effective selectivity at C9 is also observed in the methyl derivative. Thus, it is reasoned that this selectivity is due to the stabilization of a tertiary radical and the relatively low bond dissociation energy of the CH bond at a tertiary carbon. Also, the computed spin density surfaces correlate to the 90-degree rule for the reactivity of biradicals, and the methyl group at 10 and a steric hindrance at C15 correlated and explained the creation of the correct configuration at C14 and a cyclobutanol ring in a product, since anti-clockwise rotation is restricted. The fascinating synthesis of cyclobutastellettolide B demonstrated the amazing ingenuity of the Young group, and a novel strategy employing a Norris-Young cyclization could be used to synthesize natural products with similar carbon skeleton frameworks. I hope that this video has been interesting for you, and if you have any questions or suggestions on how this can be done better, feel free to put them in the comments section. The next episode will be about the synthesis of spirochelicide A and spirochelicide B by the Heritage group this year. I hope you have a great day and see you next time.